Whiplash is a serious public health issue around the world. Experts estimate that nearly 1 million people in the U.S. are injured each year in rear-end automobile collisions, with an annual cost of about $30 billion. Whiplash injuries are a modern phenomena. The term whiplash was first used in 1928, and whiplash injuries started to become more common after World War II with the rise in popularity of the automobile. Whiplash has been controversial since the 1950s, and remains so 50 years later. The greatest debate regarding whiplash today is the area of low-speed collisions, especially injuries arising from accidents with little or no visible vehicle damage. Most people are not aware that there have been literally hundreds of studies written on the problem of whiplash, and that since 1995, a number of respected scientists from around the world have made some exciting new discoveries that have uncovered how the human body can be injured in low-speed rear-end collisions. The goal of this video is to acquaint you with these discoveries, show you how low-speed rear-end collisions result in abnormal motion of the human spine, and describe some of the factors that can increase the risk of occupant injury in these collisions. This information can help us understand and treat whiplash pain, and can direct us to new ways to reduce the number of these injuries in the future. To understand the complexity of whiplash injuries, we first need to look at the basic physics of rear-end collisions. These simple concepts of physics explain how the vehicles and the occupants move during a crash. There are three concepts we need to understand: momentum, acceleration, and inertia. Momentum is simply the energy of a moving object and is mathematically described as being equal to the mass or weight of an object multiplied times its velocity or speed. From this equation we can see that the heavier an object is, or the faster it is moving, the more momentum it will have. For instance, a 2,000-pound car traveling 5 miles per hour will have only half the momentum of the same car traveling 10 miles per hour. Also, a car that weighs 2,000 pounds and traveling 10 miles per hour will have half the momentum of a 4,000-pound car traveling at 10 miles per hour. Momentum also has another important property. According to laws of physics, momentum in a collision is always conserved. That is, when two objects collide, the momentum that existed before the collision must be present after the collision. This is written as follows. As we see here, the momentum of Vehicle 1 and Vehicle 2 before the collision must equal the momentum of Vehicle 1 and Vehicle 2 after the collision. This is known as the law of conservation of momentum. Let us see how this relates to automobile crashes. First, we'll start with a car stopped at a red light. This is known as the target vehicle. It has a mass of 1,000 kilograms, but it has a velocity of 0 and therefore has a momentum of 0 as well. Now, the car behind this, known as the bullet vehicle, also has a mass of 1,000 kilograms, but is moving at 5 meters per second, or about 11 miles per hour. Therefore, before the collision, we have a momentum of 0 for the target vehicle, plus a momentum of 5,000 for the bullet vehicle, for a total momentum before the collision of 5,000. According to the law of conservation of momentum, the momentum after the collision must also be 5,000. But once the bullet vehicle strikes the target vehicle, the speeds of the two cars are different. After the collision, we find that the bullet vehicle has slowed from 5 meters per second to just 1 meter per second. Therefore, the momentum of the bullet vehicle is 1 times 1,000, or 1,000. Since the law of conservation of momentum requires that the momentum must be 5,000 after the collision, that means that the target vehicle must have a momentum of 4,000, and thus a velocity of 4 meters per second. That means that the target vehicle accelerated from 0 meters per second to 4 meters per second. Let's look at a different example, where the bullet vehicle has the same velocity as before, 5 meters per second, but weighs twice the target vehicle, or 2,000 kilograms. Instead of a momentum of 5,000, the bullet vehicle now has a momentum of 10,000. The target vehicle is again stopped and has a momentum of 0. So before the collision, we have a total momentum of 10,000. The bullet vehicle in this example slows down to 1 meter per second after the collision, resulting in a final bullet momentum of 2,000. To equal the momentum of 10,000 prior to the collision, the target vehicle must have a final momentum of 10,000 minus 2,000, or 8,000. Since the mass of the target vehicle is 1,000 pounds, the final velocity must be 8 meters per second. So, because the mass of the bullet vehicle was twice the target vehicle, even though the speed of the collision was the same as the first example, the velocity of the target vehicle has doubled from 4 meters per second to 8 meters per second. In other words, although the speed of the crash was the same, the collision was twice as severe because of the increased weight of the bullet vehicle. These two examples are simpler than what really happens during a collision, as we'll see later. But it does graphically illustrate that when we are looking at rear-end collisions, we need to not only examine the speed of the collision, but we also need to take into consideration the weight of the two vehicles involved in the crash. The second concept of physics is acceleration. It is described mathematically as delta V divided by delta T. Delta is simply the Greek symbol that means change in. So acceleration is the change in velocity of the object divided by the amount of time in which the acceleration takes place. In our earlier example describing momentum, we saw that in one instance the target vehicle accelerated from 0 meters per second to 4 meters per second. In practically every study on low-speed rear-end collisions, the amount of time that this acceleration takes place in is about 100 milliseconds, or 0.1 seconds. If we put these numbers into the equation for acceleration, we get a result of 40 meters per second squared. In the second example describing momentum, we saw that the target vehicle accelerated to 8 meters per second in the same amount of time. Thus, the acceleration in the second example is 80 meters per second squared. To simplify matters, engineers often use the term g-force as shorthand to describe acceleration. A g refers to the amount of acceleration that Earth's gravity exerts on objects. For instance, normal Earth gravity is 1g, and the complete absence of gravity is 0g, or zero gravity. Mathematically, 1g is equal to 9.8 meters per second squared. To calculate g-forces, we can simply divide the acceleration of the car, which was 40 meters per second squared in the first example, by 9.8, and we get a result of a little over 4 g's of acceleration. The final concept of physics that we need to understand when dealing with low-speed collisions is the idea of inertia. Newton's second law states that every body continues in its state of rest or uniform motion in a straight line insofar as it may be compelled to change that state by the action of some outside force. In plain English, this simply means that a stationary object will never move unless something else acts upon it to make it move. Likewise, an object that is moving will continue to move until something makes it stop moving. We can look at our earlier car crash model and see inertia at work. The target vehicle is stopped at a red light and will stay stopped until something makes it move. In this example, the bullet vehicle. Likewise, the bullet vehicle will keep moving forward until something makes it slow down. In this case, the car in front of it. And most importantly, inertia plays a critical role in how the human body moves during a crash, and is the primary reason why people get hurt in low-speed impacts. Let's now review the basics of a rear-end collision. The target vehicle is stopped at a red light. The bullet vehicle has both mass and velocity, and therefore it has momentum. The bullet vehicle strikes the target, applying an external force to the target vehicle. The target vehicle is accelerated forward rapidly. Now that we understand what happens to the cars during a rear-end collision, we can now examine the motion of the occupant inside the vehicle. First, we'll observe an animation of a rear-end collision as it appears without high-speed photography. Here it is again. Whiplash injuries take place very quickly, as you can see. The whole collision from beginning to end takes place in about 0.2 of a second, while all of the occupant motion takes only half of that time, about 1/10 of a second, or in a blink of an eye. Obviously, we'll need to slow this motion down if we are to understand what happens during a low-speed crash. We're able to do this as we have data from dozens of test collisions that have used human volunteers in low-speed crashes. These test collisions were carefully planned, and all of the occupant motions were collected via acceleration measuring devices and were photographed at speeds of 500 frames per second. This sophisticated technology allows us to observe the occupant motions during a crash in great detail. So now let's slow this collision down from 0.2 of a second to about 4 seconds. Let's now analyze this crash step by step. At the moment before the collision, our occupant is sitting upright in her seat, looking straight ahead. As the target vehicle is struck, it begins to move forward. Since the car seat is bolted to the target vehicle, it moves with the car. As we saw earlier, all objects with mass also have inertia, and the occupant's body is no exception. Since the occupant has inertia, her body is going to stay in the same position until acted upon by some outside force. In this case, the car seat back. Eventually, the car seat moves so far forward that the seat cushion is completely compressed, and the seat back begins to exert force on the occupant's lower back, and the occupant's lower back begins to move forward. Because the seat back is not perfectly vertical, the occupant's body ramps up the incline as shown here. The seat back is bending backwards at this point as it meets the resistance of the occupant. The occupant's upper back starts out farther from the car seat and moves forward later than the lower back. As the car seat reaches its greatest angle backwards, the upper torso is fully accelerated forwards with the car seat. The occupant's head, however, has no portion of the car to accelerate it forward, since this seat, like 80% of cars on the road today, does not have a proper head restraint. And since the head has inertia, it remains in the same position as it was before the impact. But the torso is moving forward rapidly. Eventually, as we can see here, the lower neck begins to pull the head forward, causing the head to rotate backwards quickly over the top of the car seat. At this point, there is a dramatic difference in how the torso and the neck are moving in relation to one another. As we can see in this graph from a crash test of 5 miles per hour, the torso accelerates much earlier than the head. In fact, the torso has mostly stopped accelerating by the time that the head reaches its peak acceleration here. Just at the moment where the head has reached its point of greatest extension, we see that the car seat begins to spring forward and move to a more upright position. Because the torso is now moving with the seat back, the spring action of the seat pulls rapidly on the lower neck, causing the head to rebound forward ahead of the torso. This results in very high peak head accelerations, as shown in this graph. As we can see, peak head accelerations increase dramatically at higher delta V's. A difference of just 1 mile per hour in delta V between 4 miles per hour and 5 miles per hour results in peak head accelerations that double. High-speed film footage was collected first in the 1950s, and scientists thought that these test collisions had found the answer to how people could be injured during a rear-end collision. The researchers saw the rapid backward motion of the spine, known as extension, and concluded that the injury was caused by hyperextension. That is, the spine extended too far back, causing injury to the joints of the spine. This hypothesis was supported by other researchers who found damage to the spine of cadavers that was consistent with this mechanism of injury. Other researchers, however, were skeptical of this theory, especially when it was applied to people who had been injured in low-speed collisions or accidents under 10 miles per hour. These skeptical researchers then measured the amount of extension that occupants experienced during test collisions and found that in low-speed crashes, the head did not extend beyond the normal range of motion of the spine. The engineers concluded that because hyperextension did not occur, injury was impossible in low-speed crashes. Another group of engineers and physicians, however, had become interested in a new line of study. These scientists realized that the occupant motion during a rear-end collision is much more complex than it seems. The complexity of a low-speed collision is evident in this chart. This data was taken from a test collision of 5 miles per hour. The first object to accelerate is the car itself, then the lower back, followed by the occupant's torso. The last thing to begin moving is the occupant's head, since the inertia of the head keeps it in place until it is moved by the torso in the car seat. Early on in whiplash research, engineers focused almost exclusively on the X-acceleration of the occupant's head. X-acceleration is that which occurs in the front-back direction, or the horizontal plane. Later, other researchers noticed that there was a degree of Z-acceleration, or in the vertical plane, when the occupant's body ramped up the car seat, but they assumed that this was unimportant. The human body is a vertical structure and is designed to absorb the force of gravity in daily life.